So we've worked out these functions for the second model, where a free fall through an atmosphere, where the air resistance is proportional to the square of the velocity. And in looking this over, I want to work the identical problem that we did a couple of videos ago, stepping out an airplane at 10,000 feet. And these were the assumptions. We've already used this one, that the initial velocity was 0. And then the initial altitude is 10,000 feet. And then furthermore, our gravitational constant, g, is minus 32 feet per second squared. And it's negative because the orientation is downward. And then the other assumption we made before was that the terminal velocity for a human would be about 180 feet per second. And so how do we express terminal velocity? It's the limit of the velocity as t goes to infinity. So you imagine that as you continue to fall, you approach this terminal velocity. And I've got it as a minus because, again, the orientation is downward. The rate of change of position going down is negative, so it's a negative velocity. Now, in thinking about all this, I came up with this earlier. I think I've got to throw a negative sign up here because the way we orient our velocity. And so I'm going to put a minus sign here. And these are a little troublesome sometimes. We have to be careful about our orientation, our frames of reference. And I got to be careful that we got the negatives and positives working correctly. So anyway, let's go with that. Now first I'm going to dispense with the terminal velocity assumption, and this will allow us to figure out what k is. And so first of all, we want to know what's the limit of a tangent function. And just ordinary tangent function, hyperbolic tangent of x, is e to the x minus e to the minus x over e to the x plus e to the minus x. And if we look at the limit as x goes to infinity of the tangent, then let's see, limit e to the x minus e to the minus x over e to the x plus e to the minus x. What's happening there is that the e to the minus x's go to 0, they shrink down to nothing, and we're left with the limit as x goes to infinity of e to the x over e to the x. Well, that would just be 1, wouldn't it? The x's cancel. So the limit of a tangent function as the argument goes to infinity would be 1. So if I go up here and use that, it's going to allow us to figure out what k is. So I have the limit as t goes to infinity of negative square root g over k tangent of parentheses square root of gk times t. Now, like we said, this tangent goes to 1, and our limit was 180 feet per second going down, and so I needed those negatives to cancel. That's why I wanted a negative up here. So the negatives cancel, and now we can figure this out. If I square both sides here, I'll get rid of these square roots, so I'll have g over k is equal to 180 squared, and now g is minus 32. So let's see, minus 32 divided by 180 squared would equal to k. So I multiplied by k and I divided by 180 squared. And I worked this out earlier. I think this is equal to minus 2 over 2025. So there we go. So let's see, we know what k is, and what is the square root of gk. So to fit everything in here, the square root of g over k would be 180, and we need to know what the square root of gk is. So it's getting a little messy here, but let me make a little more room. So I want to know what this term is. The square root of g times k would be the square root of negative 32 times minus 2 over 2025. There we go. And this would give us the square root of 64 over 2025. And that's rather convenient for us. Happily, that just turns out to be a nice fraction. 8 over 45, exactly. So let's put all this together, and I'll rewrite the velocity function. And here is that velocity function. It's minus 180 times the tangent of 8 over 45 times t, or 8t over 45. So it's a fairly clean function here. I'm going to block that off, and for this model, that's what that is. Now the other one, and I have I gotta honestly tell you, I have a little problem with this, or do I? Because if we integrate this function, we'll have a minus sign here. But I don't need a minus sign. I need that to be positive because the 1 over k is negative. So we'll see that in a minute. So I'm a little troubled by this interplay here of negatives and positives. And I think under the circumstances I'll have to figure that out later. I may reshoot this video. But for now, I need, as you'll find out in a minute, I need this term to be negative. So we'll see what happens here. Alright, so for the moment, let's assume that this is correct. And I want to use my initial altitude of 10,000, y at 0. So y at 0 would be 1 over k. Now, remember k was equal to minus 2 over 2025. And so 1 over k is going to be minus 2025 divided by 2, or minus 1012.5. So when I plug that in, I've got minus 1012.5 times the natural log of the cosh of square root of gk, recall, was 8/45 t, plus a constant. And when I let t be equal to 0, 8 times 0, this is the cosh of 0. So what is the cosh of 0? Alright, remember that the cosh of x is e to the x plus e to the minus x over 2. So the cosh of 0 would be e to the 0 plus e to the minus 0. That would be 1 plus 1 over 2. Which is 1. So this, when I plug 0 in, I'm getting the cosh of 0, which is 1, but the natural log of 1 is 0, isn't it? So all this natural log business goes to 0, and since the initial altitude is 10,000, then this part's 0, c is equal to 10,000. So turns out that my constant c is 10,000. So I'm going to do a little erasing and rewrite this function out the way it's meant to be. Okay, I've cleaned it up a little bit. I put the plus c, the 10,000 in front, and this was negative. So position function, or altitude, is 10,000 minus 1012.5 times natural log cosh 8/45 t. Alright, so we've got for this, all these assumptions, all these initial conditions for this problem. We have the position, or altitude, and velocity. And again, like I mentioned earlier, I'm a little troubled that when I integrate this, it seems like there should be a negative here, but this has to be negative. And the k is negative, so that's where the negative comes from. And because as t increases, this number increases, and I needed to subtract from 10,000. So I'm not sure at the moment what else to do about this. And let's go ahead and proceed and see what kind of results we get. So I'm going to erase this up here. and we'll start answering our questions. What happens after 10 seconds, for example? So a couple of videos ago, we looked at the problem where what happens after 10 seconds. And the velocity after 10 seconds would be minus 180 times the tanh of, and when I plug 10 in here, I have 80 over 45. 80 over 45. Now I plugged that in my calculator and I found out that I had to have this parentheses around the tanh of 80 over 45. And in fact, this number is about 0.944, so it's around 94%. That means that after 10 seconds, we reach about 94% of the terminal velocity. In this case, it comes out to right at about 170. 170.0. So the velocity is 170 feet per second going downward. Okay, now let's find out where we are. What's our altitude? So y at 0 would be 10,000 minus 1012.5 natural log cosh of 80 45ths. Alright, so I'm going to do, first of all, the cosh parentheses, 80 divided by 45. I get about 3.04. Then I'm going to take the natural log of that answer, get about 1.11, multiply it by 1012.5, and then I'll take 10,000 and subtract. So I get about 8,873.3 feet. Okay, so let's let me write those out, and I'm in a bit of okay. I still need to keep these functions. So after 10 seconds, velocity is 170.0 feet per second, and altitude is 8,873.3 feet. All right, now let's compare. The other model I wrote the numbers down, and after 10 seconds in the other model, the velocity was 149.6. And so in this model, square the velocity, looks like we're going to reach the terminal velocity quite a bit faster, and we're falling faster because in the other model, the position altitude was 9,041.4. So the comparison numbers were 9,041.4 feet for the other model, where the wind resistance was proportional velocity, and the velocity after 10 seconds was 149.6. So I thought that's kind of interesting. In this model, it looks like you fall faster. Okay, in this model. So the other question was to ask was, well, what is the how long does it take to reach the ground? How many seconds before you reach the ground? And we know pretty much that the velocity is going to be about 180 feet per second, because we're already up to 170 at 9,000 feet. So we're going to reach very, very close to terminal velocity. All right, so I want to solve that problem, and which tells me I want to know, when is this function equal to 0? Solve for t, and that will tell us how many seconds before you hit the ground, if you don't have a parachute. Alright, so I'm going to race up here and work that out. Okay, when do you hit the ground? It's when your altitude is 0. So my altitude equals 0 is when we hit the ground, and now we just have to solve for t. So I'm going to take this expression, put it over here, and then divide by 1012.5. So I have 10,000 divided by 1012.5 equals natural log cosh, and I can't seem to write cosh very well here. C-O-S-H, there we go. 8/45 t equals to, well, the equal. So I move that to the right, divided by 1012.5. Let's get rid of the natural log. And there we have it. So I have e to this number is equal to the cosh. Now my calculator comes with an inverse cosh function, and so let's, I'm going to erase this because I don't think we're going to need this now. I rewrote this a little more cleanly here, and to solve for t I need to apply the inverse cosh function. So it's going to be the inverse cosh of e to the 10,000 divided by 1012.5, and that equals to 8/45 t. If you don't have the inverse cosh function, then it's going to be a little harder, isn't it? Because you would have to write this as e to the 8/45 t plus e to the minus 8/45 t divided by 2, and then solve for t. And it can be done. It's not impossible to solve that by any means. It's just kind of a little bit messy with algebra. So let's hope that everybody out there watching this has an inverse cosh function. So I need to find mine. Go to my custom menu. Oops, my catalog first of all. And there it is, inverse cosh. I'm going to store it in this cell. So I don't know if you're able to find it and work with it nice like I am. So I got my inverse cosh, and by the way, to solve for t I need to multiply by 45/8. So the time it takes to hit the ground from 10,000 feet with these assumptions is 45/8 inverse cosh of e to the 10,000 over 1012.5. Alright, so let's see. I'm going to need, first of all, e to the 10,000 divided by 1012.5. That's approximately 19,468. I take the inverse cosh of that. So inverse cosh of the answer is about 10.56. Then times 45 divided by 8. And I get about 59.5 seconds. 59.45 if you want to go that route. Yeah, 59.45. Is that correct? Yep, 59.45. So, the object, or the person, I guess if we assume this is a person with a terminal velocity of 180 feet per second, then we should call him a person, not an object. The person hits the ground and makes quite an ugly splash of it. Hits the ground after 59.45 seconds. Alright, now I'm very confident if you plug this number into our velocity function that you're going to get a velocity that's about 179.999 something. It's going to be very, very close to 180. So you might do that just for the fun of it. Our previous model, it took 61.18 seconds to reach the ground. So a little bit faster in this model. And but there you have it. That's the free fall. Those are the free fall problems. We looked at falling through a vacuum, and then these two air resistance models. And again, the reality is somewhere between first and second power of air resistance. I don't know exactly what that is. So what else could we do with this type of problem? I suppose we could take a couple measurements and try to calculate the terminal velocity. That might make an interesting problem. So anyway, I think I'll close it off for now.